Okay, so now estimation. The estimation theory of mixed models can actually get quite advanced, so I'm going to cover this very succinctly, summarising how estimation works in principle and covering only the key concepts. So let's look at linear mixed model estimation. Stacking over n subjects, we can write the linear mixed model in matrix notation as y equals x beta plus zb plus epsilon, where the random effects and the errors have zero expectation, and the block covariance structure shown has psi for the random effects and lambda for the errors. Now, estimation is going to be by likelihood methods. The log likelihood for the marginal distribution of y being normal given x with mean x beta and covariance sigma is written in this form here. That's just the usual log likelihood for a normal random variable, but in this case in a mixed model form, or putting in the mixed model components. Optimizing that log likelihood over beta for any fixed sigma gives the result that we get here. This is the maximum likelihood estimated of beta for the linear mixed model. And this gives us x transpose sigma inverse x inverse x transpose sigma inverse y. And this is the MLE of beta, but this should also look familiar to you. If you look at the form of this estimator, this is simply a generalized least squares estimator with sigma in the middle here and here in inverse form. That's the GLS estimator we derived in lecture 6. And so the maximum likelihood estimator for the mixed model and the generalized least squares solution actually coincide here in this case. And that's important actually for linear mixed model computation. Now, to compute the estimator, we need to know sigma or have some estimate of it. And the way we proceed is via what's known as a profile log likelihood for sigma. The profile log likelihood of a parameter is obtained from the log likelihood by substituting in maximum likelihood estimators of the other parameters. So here, we take the GLS expression for beta hat and we plug it back in to the log likelihood. And that gives us the expression in definition 14. And look at what's happened. Beta no longer appears in this model because we plug in our GLS estimate. The only unknown in this model is now sigma. Everything else is observed data. So the maximum likelihood estimates of sigma, given by this term here, equal to z psi z transpose plus lambda, are then found by maximizing the profile log likelihood over the parameters that determine psi and lambda. And with the MLE estimate of sigma, we can then go ahead and form a feasible generalized least squares estimator for beta. And with both sigma hat and beta hat, we can predict the random effects using the equation that we saw earlier. This is known as the best linear unbiased predictor of beta, or the BLUP, and it just takes this form shown here. So that really, in principle, is how maximum likelihood estimation of the linear mixed model works using GLS and feasible GLS. There's just one refinement that I want to add to this. Restricted maximum likelihood or restricted estimation maximum likelihood is often used in place of ML for estimation of the linear mixed model. And the reason is that maximum likelihood estimation itself does not make the correct adjustment for the degrees of freedom lost in estimating the fixed effects of beta. And that reason it produces a biased estimate of the variance parameters. The relevant criterion for REML is this restricted log likelihood shown here in definition 16. So this is the profile log likelihood that we saw earlier, minus 1/2 the log determinant of x transpose sigma x. For the second term here is making the adjustment for the degrees of freedom lost, for the degrees of freedom we lost in estimating the fixed effects. Thus, the steps in REML estimation can be summarized as follows. 1. Find the REML estimates of sigma by maximizing the restricted log likelihood over the covariance parameters. 2. use the REML estimate of sigma to estimate beta, and 3, obtain the BLUP of B using sigma hat and beta hat, and steps 2 and 3 can be performed in a single step using what's known as the mixed model equations. And these are shown in the review slide. This is for studying your own time. Just to give you an overview, it simply restates the REML likelihood partition with the adjustment term for the degrees of freedom used in estimating the fixed effects. And it presents the mixed model equations. Given the REML estimate of sigma, the fixed and random effects can be obtained together jointly by solving the linear system shown here, a block system in beta and B, and the solutions are exactly the estimators we've already seen, the GLS form of beta and the BLUP form for the random effects.